rolling. Hi, everybody. How's it going today? Thought I opened that up already. Hopefully we're going to get through all of section 5.3 today. Let's cross our fingers. If we need to, we can do just a little bit more tomorrow. And then the rest of tomorrow will be a work day. Does that sound good? And then I know it seems like weird. I mean, it's not really like having homework over spring break, but like I'll just make the section 5.3 assignment due like the Monday we get back midnight. Does that sound good? Okay. So let's get to it. This is kind of an interesting section. The section name at least. The fundamental theorem of calculus. The fundamental. It sounds so groundbreaking. It sounds so like.
It really does.
Like the fundamental. The fundamental theorem of calculus. Not just any. This is the fundamental theorem of calculus, and the book says it's appropriately named. It's the fundamental theorem of calculus is appropriately named because it establishes the connection between differential calculus and integral calculus. And you know, kind of already learned it. We kind of already learned that the antiderivative is really equal to the integral. So that's how it's kind of meshing here. It's going to connect what we know about antiderivatives and what we know about integrals and put them together. So knowing what we know about derivatives and knowing what we know about integrals, so kind of tie it all hand in hand. It gives you a little bit of background. I won't bore you with the details there, but basically this is what we're going to be looking at here. So we've got some sort of g of x is equal to a going from a to x of f of t dt. Okay, so this is an integral, and I got a graph of it down below. It might be easier to visualize here. So say you've got some function not dependent on x. Notice that. The function is not dependent on x. It's f of t, okay? So some function, going up, down, varying, whatever. We got some function going on, and I am going to say, now I'm not just going from a to b. So this is kind of like what Caleb and I were talking about the other day. Not just going from a to b, not just going at a definite place. Now it's saying, okay, going from a to x, some spot in there, okay? So going from a to some value x, and say, okay, it's going to vary in there. That's my x value. That's my independent variable. That's what's going to vary. So what we're going to do is say, okay, going from a to x of f of t dt, we're going to establish a connection between them. We're going to say, okay, if g of x is some function, how do we find a value? How do we create an equation to represent what that area is really going to give us? If I change that x value and I give you a definite x value, I want to be able to plug in that x value and know what my area is going to be. And that's what we're going to be looking at here. So let's kind of investigate it a little bit. If f is the function whose graph is shown in figure 2, and g of x is equal to the integral from 0 to x of f of t dt, find the values of g of 0, g of 1, g of 2, g of 3, g of 4, g of 5, and then we're going to sketch the graph. Basically what we're doing here is we're saying, okay, we have no idea what it's going to look like in the end, so let's just plot some points. Because that's what we really do when we don't understand what something's going to behave like. We just poke a stick at it, we plot some points and see what's going to happen. So let's do that. I mean, we know how to evaluate these things, right? We're going to say, well, g of 0, and this is f of t. This function that we got, this weird one that like pauses in, from 1 to 2 and then curves from 2 to 5. That's f of t. Notice that I'm giving you x values, not t values. I don't really care what the dependent variable of the function is. I care about the fact that my interval is changing. That's what's changing. That's my independent variable of my g of x. So if I say g of 0, that's like saying, well, what's the area underneath the curve at 0? Is there area underneath the curve at 0? No. So g of 0 is 0. Okay, g of 1. So I'm just going to, geometrically figure out what the area is here. So g of 1, this is going to be a triangle. I got this area here underneath the curve, that triangle, 1/2 base times height, 1/2 1 times 2, so 1. And then I'm going to keep adding on areas. So I want g of 2. So g of 2, and I hope we understand, I could write it out as the notation. In my notes, I had written it out as the notation each time. What I'm saying here is, okay, I want the integral from 0 to 2 of f of t dt. Right? That's the notation that I'm looking at here. The integral going from 0 to 2 of f of t dt. And I could have written that out for g of 0 and g of 1 as well. So going from 0 to 2, well, I'm just going to add on those two boxes. So total of 3 now. So g of 2 is 3. So g of 3 is going to turn into the integral from 0 to 3 of f of t dt. All right, well, let's add on some boxes. Now, this is kind of a tricky part here because it looks like it's going to curve, so we kind of have to estimate it a little bit. Does it look like it's, if this was going straight down, it would have been, another 1, right? But this is curving down, right? If this was a triangle, the area would just be 1, but it's curving down. It's going a little bit more than just a triangle. Like if I put a straight line in there, I'm missing some of that area out there. So let's estimate it to be like 1.3. That's what the book estimates it to be, but 1.3. So 4.3 altogether. And that's an estimation here. And now, when I take g of 4, when I go from 0 to 4 of f of t dt, what's going to happen to my area now? What's going to happen to my output? It's going to start to go down because the function has gone below the x-axis. So now I have to start to take into account negative area. Well, this looks pretty symmetrical, and I just estimated that area to be 1.3. So I'm just going to take off that 1.3 that I just had. Okay? Because this was a total of 4.3 minus my 1.3. And then it looks like it's going to be, again, symmetrical. So g of 5 now, the integral going from 0 to 5 of f of t dt. Well, it looks like that's going to give me another 1.3 if I'm going to estimate it to be 1.3 in the negative direction, right? So therefore, I went 3, total net value of 3. I decrease it by 1.3. Looks like it's about 1.7. Do you see how I'm finding area, but I'm really giving myself inputs and outputs? G of 0 is 0. G of 1 is 1. G of 2 is 3. G of 3 is 4.3. G of 4 is 3. G of 5 is 1.7. Let's see what it looks like. Let's see what this thing looks like. I'm going to graph it in red here. 0, 0, 1, 1. And I think I'm going to have to go up a little bit. 2, comma 3. Let me extend this up a little bit. Okay, here's like one value here. Somewhere up there. How much should we go up to? 4.3? There's 1, 2, 3, 4. We'll be able to ballpark it from there. Okay, so here's 1, comma 1. There's 2, comma 3. And then here's 3, comma 4.3. Just a little bit above 4. And then it starts to come down. G of 4 is 3. G of 5 is 1.7. Somewhere in there. There's my function. There's my g of x. So if g of x is equal to the integral, what do you notice about g of x? What do you notice about the maximum value of g of x? It's a 0 of what? Of f of t. I don't want to call it original anymore because now we're going to look at antiderivative and stuff. So I'm going to say it's the 0 of f of t, right? The maximum value of g of x is the 0 of f of t, which leads me to believe that if I've got g of x and I take the derivative of g of x, that's going to give me f of t, right? I just made a very powerful statement right there. I said that if I take the derivative of g of x, that's going to give me f of t. That is actually fundamental theorem of calculus part 1. Okay? If I take my derivative of g of x, that's going to give me f of t. But it's going to replace my value. It's going to replace my f of t with f of x. So go ahead and take a look here. I would write this down. That's pretty important. It is the fundamental theorem of calculus. If f is continuous on a to b, then the function g is defined to be g of x is equal to the integral from a to x of f of t dt. And it's continuous on a to b and differential on a to b, and this is the important part here, g prime of x is equal to f of x. G prime of x is equal to f of x. If you say that g is the integral of f of x, then g prime is f of x. If you say that g of x is the integral of f of t, basically g is the integral of f, then g prime is f. You can differentiate g to get f. That's what we're saying here. And that's what we saw in that graph. We saw that maximum value coming up. And if we took the derivative of that red function that we had on the last slide, that means that it would reach its maximum point, which would mean that I would have a 0 in the derivative. So g prime of x was going to give us f. So really, the only thing that's going to change here, this is just another notation to write it down below before I move on. And whenever you see this notation here in the book, FTC1 or FTC2, that's really referring to this theorem. FTC1 is fundamental theorem of calculus part 1. FTC2 is fundamental theorem of calculus part 2. And spoiler alert, we already know what part 2 is. That's the thing with the line and the antiderivative and stuff, but we'll get there in a second. So using Leibniz notation for the derivatives, we can write it as this. If you take the derivative of the integral, which in our mind should think, well, that's going to be we're taking a derivative of an integral. But aren't those two things opposites? Isn't taking the derivative of an integral kind of like multiplying the dividing, kind of like adding the subtracting? They're inverses of one another, aren't they? So they're essentially going to cancel each other out. This is basically going to cancel each other out. And you know what's going to happen? You're going to take x and plug it into the input for f. Okay? D over dx is going to cancel out the integral. It's going to undo it. Okay? So it's going to cancel that out. And what's going to happen is you're going to take that input value, that x value, that thing that was changing in terms of my interval, the thing that was changing in terms of my left and right, and that's going to be input into my function. That's going to be inputted into my function. So let's take a look here. Find the derivative of the function g of x is equal to the integral from 0 to x of square root of 1 plus t squared. So we just got done saying that g prime is equal to f, right? G prime is equal to f of x. G prime is equal to f of x. So if I want to find the derivative of g, I'm really just looking to find g prime, right? I'm really just looking to find g prime. And g prime of x is really just f of x. Well, what's f in this case? Yeah, square root of 1 plus t squared. So if I want f of x, essentially all I'm going to do is take 1 plus x squared. The dt goes away, right? Taking the derivative undoes the integral. So it's going to be that g prime is just straight up going to be the square root of 1 plus x squared. So what's going to happen here is this is essentially going to get plugged in for that. Essentially, that's all that's going to happen. That x value is just going to get plugged in for that. Yeah, I'm going to do one more of these. I'm just going to write this in. So you're one of the people that likes to print out my notes. This is not in there. So if I say g of x is the integral from 0 to, let's say 2 to x squared. 2 to x squared. Of the square root of t plus 3 dt. And I wanted to find the derivative of that. Now, I hope we understand that the 2 is not even really going to matter in this case. Okay? My starting value is not even really going to matter because I'm looking at area. Like the horizontal shift of it's not really going to change anything. because I'm looking for a function that just defines my derivative. So the starting value doesn't really matter, but what's weird in this case is the fact that I've got an x squared up here, and it's, are you all right? Are you okay? Can you take a minute? Okay. What's weird is that we don't just have an x, we have an x squared up as my endpoint.
I just choked on my air.
Choked on air. That's so hard to do. So g prime of x is going to be equal to the square root of, so I plug x squared in, x squared plus 3. But because there was a function within a function, what I have to do is I actually have to perform a chain rule. Okay, I not only take the derivative of this, which essentially cancels out the integral, but I also take the derivative of this. Well, what's the derivative of x squared? 2x. Okay, so g prime of x is equal to 2x square root of x squared plus 3. Okay, so moral of the story there is if that x changes into anything else, if that x changes into x squared, if that x changes into 2x plus 3, if that x changes into anything else, ln of x, you have to take the derivative of that thing. Not only plug it in, plugging it in is taking the derivative of the integral. But you not only need to take the derivative of the integral, but you also have to take the derivative of this thing up there too. And that's why we had to multiply in the two x's. Let's do another one of those because that's kind of tricky. And heck, let's do a trig one because do I even have to change the function at all? Just sitting in there? No. So I could make this any sort of wacky function I wanted. Please don't. Okay. But isn't this notation just saying find the derivative again? I'm just changing up the notation. I'm not saying find the derivative. I'm just actually using find d over dx, which we know to be find the derivative. That's just another way to say that. D over dx of that thing. Well, so if I want to find the derivative, well, that's just going to be plugging that in. So secant x to the 4th times what? 4x to the 3rd. Right? So I'll just put it in front because that's how we normally write it. There's my answer. Yeah, g prime. It doesn't define it as g, but yeah, sure, you can write it as g prime of x. Yeah, that's the derivative. That's the derivative. Okay? So when you've got a function up in the integral, it's kind of like the fact that you have to take the chain rule. You got to take the derivative of what's ever in the top and multiply it onto the end. All right. So fundamental theorem of calculus, part 2. Part 2 is something that we already know. Something that I kind of taught you ahead of time a little bit. It's that vertical line thing that we talked about. It says that if f is continuous on a to b, then the integral from a to b of f of x dx is actually equal to capital F of b minus capital F of a. We use this special type of notation, and I'll write it out so we can see it here. A to b of fx dx is equal to capital F of x b to a. Which we know to be f of b minus f of a. And what is capital F? The antiderivative. Right? Capital F is the antiderivative. If f is continuous on a to b, then the integral from a to b of f of x dx is really equal to capital F of b minus capital F of a, where f is the antiderivative of f. That is to say that if I take out prime, that's going to get us back to f. Right? If I take the derivative of capital F, if I take the derivative of the antiderivative, it's going to get us back to f. Okay, we're going to use this. I'm going to use this notation a lot. The book sometimes puts brackets on this. It makes it look like that. have always learned it without those brackets there, so that I've just gotten accustomed to write it like that. But if you see it in the book where there's bracket symbols on it, that's the same thing, okay? So let's do some. So we're going to evaluate the integral from 1 to 3. You know, if I'm thinking back to what we've done before, if I'm asked to find an integral, there's really only 2 ways we know how to do this right now. We could either graph it to find it, and sometimes I ask you within the directions, graph so that we can find it. Like geometrically find it, like with those triangles and stuff like that, or some other way, like in the last section. Or do fundamental theorem of calculus part 2. And again, it's if you ever see it in the book, it might say FTC2. Okay, that is this thing. That's FTC2. All right, so let's try it. Okay, I'm going to evaluate the integral of 1 to 3 ex dx, which is, okay, what's the antiderivative of e to the x? E to the x, that's that special one that doesn't change ever. So e to the x, we use my vertical line 3 to 1, which means that's e to the 3rd minus e to the 1st, right? Plug in 3 minus plug in 1, right? Now, is this e to the 2nd? No. That would be e to the 3rd over e to the 1st, right? It's very tempting to try to say that. So let's just figure out, I mean, you could leave it like that. That's the simplified version. But I'm going to go to my calculator and figure out the decimal value, e to the 3rd. The book actually leaves that as the answer. E to the 3rd minus e to the 1st is 17.37. And remember, that's the area underneath the curve. Think about e to the x, you know, the exponential function, e to the x. And I'm going from 1 to 3. It's 17.37 units underneath, going from 1 to 3, underneath the curve to the x-axis. That's the area underneath that curve. Again, I'm going to add in another one here. We'll do another example here. Let's go 2 to 5 of x squared plus 5 dx. We're going to evaluate that. If I don't tell you what to use, always try to use FTC2. Always try to use this fundamental theorem of calculus 2, because that's the easiest route to take. Now, when can you not use this? Well, when something's not very easy to find the antiderivative of. Like, for example, this. Can we pretty easily find the antiderivative of that? Yeah. So we'll use this method. So we're going to say that's going to be equal to x to the 3rd, pick it up 1, divided by that thing, plus 5x, 5 and 2. And now we plug in 5, then we plug in 2. So this is going to be equal to 5 to the 3rd over 3 plus 5 times 5 minus, I'm going to put it in big parentheses because sometimes we forget to subtract. So 2 to the 3rd over 3 plus 5 times 2. And a lot of times, I don't know why, I like to do this and then I like to do that and then I subtract them. That's what you'll see here. 5 to the 3rd divided by 3 plus 5 times 5 is 25. 66.6, nice. Minus, and this is going to be 2 to the 3rd over 3, so 8/3 plus 10. So 12.6 repeating. So that's going to get me 54, all in total. Make sense? Do we understand what this is replacing? I hope you comprehend, I hope you understand, like, think back to section 5.1. To calculate from 2 to 5, I would need to find the Riemann sum between 2 to 5 of this x squared plus 5x. So I would need to find the limit as n approaches infinity of each of those little strips. Or I would have to do the the right side or left side approximation with rectangles. Like this is kind of taking care of all that work for us. Like I hope we understand how much work this is saving. Pretty nice. Find the area underneath the parabola of y is equal to x squared from 0 to 1. I hope we can understand that this transfers from words into this notation. Okay, if I'm going 0 to 1, that's my integral. And if I want the area underneath my curve, I want to calculate what the integral is. The integral of x squared dx. And I got to be honest, that's pretty easy if we know fundamental theorem of calculus 2. That tells us we can do x to the third over 3 of 1 to 0. And man, is it nice when we get a 0 as the starting value. Because now what we can do is just say, oh, 1 to the third over 3 minus 0. So just 1/3. Remember that big long proof that we did in section 5.1? Yeah, remember when we ended with 1/3? Yeah, remember that? We just did that all in like 2 seconds, right? Because of the fundamental theorem of calculus 2. So nice, right? So convenient. That's a good word for it, convenient. Okay, this looks funky. I've got dx in the numerator. What? Okay, don't let it confuse you. If I want to evaluate this from 3 to 6, well, dx over x, isn't that like just 3 to 6 of 1 over x times dx? And now that makes a little bit more sense. So what's my function that I'm going to find the antiderivative of? Right, it's 1 over x, which is going to get us to ln of absolute value of x. Okay, so this is going to be ln of absolute value of x from 6 to 3. Do I have to worry about the absolute value? No, because they're both positive. Don't need to worry about that. So that's going to be ln of 6 minus ln of 3. And this one, we can use our properties of logarithms to say subtraction means division. This is ln of 6 over 3, which is ln of 2. Which, I mean, I guess we could have just done the subtraction in our calculators too. But ln of 2 is 0.693. Yes? Yep. Yep. Because algebraically, those things are equivalent. So, yeah, it should. Unless your calculator's messed up or something. Calculator's broken. Let's do another one. Find the area under the cosine curve from 0 to b, where 0 is in between b, or sorry, where b is in between 0 and pi over 2. Yes?
The last one, I missed. Why did you say we don't have to do anything with the d of x?
That is part of the notation that gets canceled out when we take the derivative. Yeah. When we take the antiderivative. Okay. Because the notation says, when you find the antiderivative, all of that underlying stuff goes away. Okay, that's the process of finding the antiderivative. Okay. Let's go back. Yeah. Find the area under the cosine curve from 0 to b, where b is between 0 and pi over 2. So honestly, here's what we need to do. where the notation says do this. Dx, whoops. Right? What's the antiderivative of cosine? Negative sine. So this is going to be, right? It's negative sine, right? Negative sine. I didn't write the negative in there. That's wrong, right? Okay, good. I think that's wrong. So that means that's negative sine of x from 0 to b. Is it positive sine?
Isn't it? The positive sign of x gives you cosine.
Yeah, it's negative sine that gets you.
Cosine of
Okay,
x,
now I have to think about it.
negative sign.
Let's think about it. This is always the tricky one. Because the derivative of sine is cosine. Yeah. So this should be a positive.
Yeah.
This should be a positive. You know, you can always check that. That's why I pulled out this thing. You can always check to see, okay, did I calculate this correctly? Because if I take the derivative of this, it should get us back to this. So what is the derivative of sine? It's just cosine, right? So you can always check yourself if you'd like to. All right, so again, why is it nice when we take 0 to b? Well, this is sine of b minus sine of 0. What is sine of 0? 0. So it ends up just being sine of b. Why did we have to restrict from 0 to 2 pi over 2? Well, because I think the b would have gone, something would have been weird about the b being pi over 2. But really, all I needed here was this stuff. Yeah. And that's what you'll see on the later parts of the homework. It's gonna ask you not just going from number to number, it's gonna start putting variables in there too, so you can actually just write it out what those variables end up being within the notation. Let's do one more like this. What is wrong with this calculation? See, another reason why I wanted to put this problem up here is because you see the brackets here? That's the way the book is going to show our vertical line, okay? So what's wrong with those? First off, let's see if there's anything wrong with it. Let's take it step by step. Let's try to evaluate from -1 to 3 of 1 over x squared dx. Well, I like to write it as just an exponent. So this is really like saying from -1 to +3 of x to the -2nd, right? dx. So now let's take the antiderivative. Well, the antiderivative is kicking it up 1, x to the -1, and then dividing by that thing, right? Which is essentially, and that's 3 to -1 now, what exactly the same thing that they had, right? So far, is their calculation good? Okay. Now, I'm just going to reduce that a little bit. Dividing by -1 is the same thing as just putting a negative out front. Okay. All right. So top minus bottom, -3 to the -1 minus -1 to the -1. And that negative is sitting out front, right? I guess it doesn't matter because it's an odd power. Okay. So let's see what happens here. This is -1/3 minus a -1, right? Because putting that into the denominator would have made it the same. We all agree? So do we see here what the issue is? They must have messed up with the negative right here. Another issue. The book gives us another issue. Think about 1 over x squared. Where is it undefined? At 0. So is this function truly continuous from -1 to 3, which was one of the conditions for using the fundamental theorem of calculus? So essentially, guess what? The fundamental theorem of calculus doesn't even hold for this stuff. That's another big issue that we have here, is that because there's a there's a discontinuity in there, right? There's a vertical asymptote in there. This function is not even, we can't even use the fundamental theorem of calculus on it because it's not defined at one point within the interval from -1 to 3. I could use it from, like 1 to 3, that would have been fine. Or like from -1 to, like -2 to -1, that would have been fine because there's no discontinuity in there. But there's a discontinuity in here. So that's another issue with this problem. This last slide, I don't necessarily even I don't even think there's anything new on this last slide. It's just kind of like summarizing things for us. It's just kind of like a reminder that differentiation and integration are inverse processes of one another, right? Because we can link them together with the antiderivative, you can think of differentiation and integration kind of like how you think of square rooting and squaring something, kind of like how you think of division and multiplication. They are inverse processes of one another, right? So that we can put those two fundamental theorem of calculus part 1 and part 2 together to say that, okay, if you want to find the derivative of an integral, it gives you back the function. If you want to find the integral, it gives you the antiderivative, right? It kind of works itself backward, okay, of those two functions. Yeah. I don't think I even need to talk about the part below. Pretty cool, right?
Yeah.
Pretty nice and easy. All right. So long, everybody playing along at home. I'll see you later.